Welcome to 8.8 improper integrals, and we're going to look at integration with infinite limits. All right, so one thing we need to do is we need to kind of remind ourselves of a theorem from chapter 4, that continuity implies integrability. So if a function f is continuous on the closed interval, then f is integrable on that closed interval. So that means we can integrate from a to b of that function, and it exists. So what happens when integrals don't satisfy this? All right, so what does that mean? So we're going to look at improper integrals with infinite integration limits. All right, so if we have a finite closed interval, a to b, it rules out this fact that we're going from a to infinity. We're just looking on this closed interval, so it's no big deal. We can handle that. All right, continuous, right? If we have a continuous, this rules out this guy because we're not continuous at x equals 2. So how do we deal with something like this, right? So for instance, our goal today is to essentially find the area under a curve. That's what an integral is. And if we're looking at this curve here, which is 1 over x, and if we're going from 1 to infinity, how do we figure that out? All right, so what we have to do is anything with infinity, we convert to a limit. So what does that look like? All right, and then we'll get into some other vocabulary and important pieces over on the left here. So if I'm going, or if I'm integrating f from a to infinity, then what we're going to convert this to is we're going to convert it to a limit where b approaches infinity, and now we're going to integrate from a to b of that function, and then we'll see where that takes us. So before we kind of keep going, I want to bring us over to this, okay? So remind yourself that if the limit as x approaches c of f of x equals plus or minus infinity, we would call that diverging, okay? We would say f of x diverges. Well, the same kind of goes here. If our limit, after we go through and integrate, if we get plus or minus infinity, we would call that a diverging integral, okay? So now if we're talking about improper integrals, if the limit exists, then the improper integral converges. If the limit does not exist, then it diverges. So we're going to be using this vocabulary, okay? So now kind of going back to the other two portions of these improper integrals, if I'm integrating from negative infinity to b of that function, we would change it to the limit as a approaches negative infinity, and now we write a as part of our integral, okay? So we treat it as if it is a closed interval, okay? But then we go through and we take the limit of that after we go through the integration portion. Now the last piece is if we're going from negative infinity to infinity, okay? We are going to break this up into two pieces, all right? So we would break up the first integral from negative infinity to c plus from c to infinity, and then we would set up our limits integrating those accordingly, either like this form first or this form second. Now, if either one of these diverges, then we could say the whole thing diverges. So we don't necessarily need to test both of these right from the beginning, and you'll see that in an example. So let's go ahead and straight to our first example over here, okay? So we are integrating from 2 to infinity of dx over x minus 1 squared. Now, x minus 1 squared, this graph is going to look like so. And we want to go from 2 to infinity. So we want to find the area under this curve forever, after starting at 2. Okay? So this is just the calculator portion. We'll come back to that in a second. But how do we go ahead and set this up? Well, since we have that improper integral, I know I'm going to change it from the limit as b approaches infinity. And now notice we change our limit of integration there. So now instead of infinity, we have the integral from 2 to b. And now we can integrate this as we normally would. So we would do a u substitution. U is x minus 1. So then du is dx. So now the limit continues all the way through until we're ready to actually take the limit. Now notice, since we have that u substitution, I'm changing my limits of 1 over u squared. We can integrate this, right? And we, again, still have the limit as b approaches infinity of negative u to the negative 1, still from c to d, but now we're substituting back in, and now I'm changing my limits. So now we can go ahead and evaluate the integral, okay? So now we've evaluated the integral. I plug b in, I plug 2 in, okay? And notice, when we plug the 2 in, it's minus a negative, so that's where we get the plus from. Now we're in terms of b. So now we can do our straight substitution for our limit and evaluate this limit. So when we plug infinity in, right, where does that lead us? Well, we get negative 1 over infinity plus 1, because that's this piece. So 1 over infinity is 0. Plus 1, we get 1. So we would say that this integral converges, and it converges to 1. So really, what is that saying? Now kind of going back to the calculator, notice if we plug in this really big value for where we're integrating from, and we're essentially finding the area under this curve from 2 to this really big number, you're going to see the calculator gets really, really close to 1, and that's what we just showed here. All right? So now I want you to try this next example, example 2. Okay, I'm going to get you started, but I want you to finish this off and see what your conclusion is. All right? So we're taking the integral from 2 to infinity of dx over x minus 1. Well, since we have this improper integral, I need to change it to a limit as b approaches infinity of 2 to b, dx over x minus 1. We now can integrate this guy. So we're going to use our u substitution, and we get here, notice the change of our limits. All right, go ahead, finish this example off, come back and check when you're done. Okay, so how'd you do? So integrating u to the negative 1, we get ln of u. I notice our integration limits still stay c to d, but when we substitute back, we're back to from 2 to b is where we're going to integrate. Now remember, use proper notation. This limit comes with us all the way through. All right, so now we can evaluate this portion when we plug b and 2 in. Okay, so as we integrate, or evaluate, I should say, one thing we need to note is I made a mistake. This should be a minus, not a plus. So change that. All right, and so we're just evaluating it from 2 to b. And now we can substitute in. So when we substitute infinity in for b, we get the natural log of infinity minus 1, which is just infinity, and minus the natural log of 1, which is just 0. So this goes to infinity, and therefore we can say the integral diverges. Let's try one more example on the back. Okay, I lied. 2 more examples. Sorry about that, you guys. So we need to talk about some discontinuities and some overview here. So if f is continuous on a to b, but not at b, right? We would then rewrite this as the integral from a to b, all right, of f of x equals the limit as t approaches b from the left. So b is that right endpoint, and it's not continuous at that point. So we're going to rewrite our integral as the limit from t, as t goes to b from the left of the integral from a to t of f of x. Okay, now similarly, if f is continuous on the interval open at a but closed at b, meaning not continuous at a, then the integral from a to b, we're going to rewrite it as a limit as well, but this time it's the limit as t approaches a from the right, because that's the left endpoint. So we want to approach it from the right and go towards the left. of the integral from t to b. So just some things to kind of look at. So again, up above, if it's not continuous at b, we're going to change that guy. All right. If it's not continuous at a, we're going to change that lower limit. All right. Now, what if we have f continuous on the closed interval, but not at some point c that's within that interval? Okay. So we're going to break this integral up from a to b, and we're going to say, okay, we're going to rewrite it as the integral from a to c of f of x plus the integral from c to b, and then we're going to rewrite each of those accordingly. So let's look at our first example here, okay, and we'll go from there. All right, so now we're looking at this definite integral, but we're only continuous from 0 to 3, not including 3, right? Because when we plug 3 in, we get 0 in the denominator. So we need to rewrite this as the limit as b goes to 3 from the left, from 0, or of the integral from 0 to b, and now we can integrate this. So again, we would have that u substitution, so hopefully the integration aspect isn't a big deal for us. So then we're integrating, all right, and we get negative 2u to the 1/2. Don't forget to bring the limit on down, and now we can evaluate from 0 to b, and when we do, all right, we're going to get the limit as b goes to 3 from the left of this information here, negative 2 root 3 minus b plus 2 root 3. Now we can substitute b for, or 3 for b, all right, and when we do, this portion goes to 0, and we're just left with 2 root 3. So this integral actually converges to 2 root 3. All right, let's take a look at this next example here. Okay, so now we're going to take the integral from 0 to 4 of dx over x minus 3 squared. So what should we notice? This function is continuous on that closed interval except when x equals 3. So we need to split up this integral. All right, so we're going to start from the integral from 0 to 3 of that function plus the integral from 3 to 4 of that function. And now we just have to write it in terms of those limits, similar to the discontinuities overview up above. So we're going to rewrite this guy as the limit as b goes to 3 from the left of 0 to b of that function, plus the limit as a goes to 3 from the right, because that's the left-hand endpoint, of the integral from a to 4 of that function. Now, we can go ahead and use a u substitution for both of these, all right? But I'm just going to focus on this first one, all right? Just for the starting part, all right? And remember, because if this diverges, then the whole thing diverges. So I don't even need to worry about that other limit. But if it converges, then I have to go through and work through that other limit on the right, okay? So we only need to focus on one part unless it converges, okay? So as we go through, I'm going to focus on that first limit as b goes to 3 from the left, and we're going to integrate. And when we integrate, we get negative u to the negative 1. Substituting back, we can now evaluate this integral from 0 to b and plug in, okay? So now we can use that substitution. I'm going to let b equal 3, all right? And when we do, we're going to get 1 over 0 plus negative 1/3, okay? So 1 over 0 just goes to infinity. Infinity minus 1/3 is still infinity. So since this piece diverges, I don't need to go through that second integral or that second limit, okay? Since this piece diverges, the entire thing diverges, all right? So if I found that this did converge, I'd have to go back up to the top and work through that second integral, that second limit, to see what happens there and then make my final conclusion. But since it diverges, I know the whole thing is going to diverge. If you have questions, let me know.